Hello everybody, welcome to the Henstitute. In this video we're going to take a look at this Kirchhoffs rules problem in which you have your battery connected to your headlights as well as the alternator, and the battery has a certain resistance on it, the alternator has a resistance, and the headlights have resistance. So we have two different voltage sources here, our battery and our alternator, and we've got three different resistors. So the circuit kind of looks like this over here. And we're going to go through how would I find the current IA, the current IB, and the current IH. So basically how much current is going through the battery, how much current is going through the alternator, how much current is going through the headlamps. The first rule, number one, is what we call the loop or the junction rule. Sorry. And basically it says that all the currents going into a junction have to equal all the currents going out of a junction. So looking at the way this is pictured, I have IB and IA going into this point over here, and then I have IH coming out. So if I was going to write the junction rule, I would write that IA, the current through the alternator, plus IB, the current through the battery, should equal IH, the current through the headlamps. Now, I can do it for a whole bunch of different junctions. I don't really need to. And these currents are something that you would actually pick. You would actually kind of figure out what direction things are going. And the way I usually suggest it is to make loops. So you might do a certain loop to kind of come out, but these currents are kind of set up based off of the battery, the positive side here, it kind of indicates that the current should go this way, and the positive side of the alternator kind of indicates that. And then since you had those two going into this junction, we got to have something coming out. So that's where IH came from. The second one is what's known as the loop rule. And this one is going to create more setups. And the way you do this is technically you would have three different loops you could actually look at. And you just pick a direction for these loops. It doesn't really matter what direction you want to pick. And you're usually trying to follow the current as best you can. So for example, up here, I might make the loop go in this direction, go clockwise. So if I call that A, actually let's call this Z. Here. So this loop up here is going clockwise, and that might be one of them. Another one of the loops could be this loop down here. Now, since both the current IA and IB are going to the left, you have to kind of pick a direction. It doesn't really matter. I typically always go with whatever has the most voltage, so I would probably make this go clockwise as well. So I'm going to call this one Y, and then I'm going to make the big loop on the outside as well. And I'm going to call this one W and I'm going to make them all go clockwise. So what you do is you mention that all the voltage sources should equal all the voltage drops. That's the way I usually think of it. So if I start with W, for example, loop W, I have only one voltage source. I have the 14 volts, and I'm coming out of the positive on it, so it's going to be a positive. And it should equal all the voltage drops. So the drops are the current times a resistance. So I have IA times 0.1 plus, as I come up here to this lamp, I have IH times 1.2. I'm going to get rid of this little V here. I don't want you to think that that's another thing. So there's one. The problem is I don't know what IA or IH is, so I can't solve that. I actually have three unknowns, so eventually I need three equations to actually solve this. So we're going to do a system of equations here. So let's go to Y. It's another one. This one's a little bit different. So I'm coming out of the positive. I went clockwise around this one. So I'm coming out of the positive on my alternator. So that's a positive 12 or 14. But if I kind of follow, I'm going backwards through this one. So I'm actually going to come out of the negative on this source. So I'm going to actually add to it a negative 12. So in other words, my two things are working against each other in this particular case. And then my currents, I have IA times the 0.1 plus I have IB times a 0.01. Now the only weird part is I actually went backwards through IB. So IB I had already designated as going to the left based on this little rule up here. So I have to stick with that. So if I go the opposite way, I'm actually going to make it negative down here. So instead of actually adding them together, I'm going to end up subtracting them. The only reason I'm subtracting is because it's going the opposite way from what I picked. I don't want to change in the middle of this. Last but not least, I'm going to make one more. I don't actually need this one. I just need 3, but I'm going to make 4 total equations. I'm just following Kirchhoffs rules. So this one is this top loop up here. It only has a 12-volt source. It's going to equal, I'm going the correct direction through IB, so it's IB times 0.01, plus I'm going the correct direction through IH, so IH times 1.2. Then it's a matter of how do I solve a system of equations. And when I do that, I look for ways to kind of eliminate stuff. Now, I can do some substituting with the junction rule up here. That's an easy one to kind of work with and have some fun with that. I often sometimes like to combine some equations to try to get other things. However, I want to kind of show something. If I combine z and y here, in other words, I add these 2 equations, my first instinct is, hey, look, the IBs are going to cancel. That's awesome. But if you notice, also the 12s are going to cancel. And guess what you're going to end up with? You're just going to end up with W up here. So that's not going to get us anywhere. What I really need to do is I need to take this junction rule and do some substituting. Just for simplicity's sake, what I'm going to do is I'm going to substitute that IH is IA plus IB into the W equation. So that's going to make my new W look like this. It's going to be 14 equals IA times 0.1 plus I'm going to have IA times 1.2 plus IB times 1.2. Once I get it like this, then I can combine these 2 together and basically say that I have 14 equals IA times 1.3 plus IB times 1.2. You go, okay, that didn't get me anywhere. I still have one that has IA and IB. So now what I typically do is I come over here and I look at my other 2 loop rules that I haven't used. So I've used this one, I've used this one, so I'm kind of checking them off, and I say, is there any of them that have something that I could kind of combine? I'm trying to think of this in terms of a system of equations and how do I minimize that. Now I know some of you are really good at system of equations. I tend to use substitution and elimination. Those are the 2 I'm going to use. I'm not going to use matrices. I'm not going to graph it. So the one I notice is Y here has an IA and an IB in it, so I'm going to actually use this one down here. So I'm going to simplify this. 14 plus a negative 12 is going to be 2. So I'm going to write this as a red. So this is my new, this is Y down here. So this is 2 equals, and I have IA times 0.1 minus IB times 0.01. And that came from up here. Now, when I look at this, since it's already subtracting this IB, I think the easiest method is there a way that I can make these have the same? So as I kind of do that, I think, okay, what can I multiply by 0.01 to make it be 1.2? So if I think about it, I want to multiply by 120. So this is going to seem weird, but I'm going to take this equation and multiply it by 120. When I do that, that's going to make this, so remember, everything has to be multiplied. So 120 times 0.01 is going to give me a negative IB times 1.2, which is awesome because that's going to cancel. Those are going to cancel there. And then I have 120 times this, so this is going to make it this IA times 12. And then I also have to take the 2 over here times 120, so that's going to make this 240. So now I have a brand new version of y where I basically just multiplied both sides by 120, but I can combine it, so I can add these two equations together to eliminate the IBs. When I do that, the IBs will go away. Bye-bye IBs. I have IA 1.3 and 12, so that's going to basically be IA times 13.3. And that should equal, I've got 14 plus 240, so that's going to make this 254. Then I just divide by 13.3. And finally, I get that IA is going to equal whatever that comes out to be, 254 divided by 13.3. And I get 19.09, blah, blah, blah. So just for simplicity's sake, I'll say 19.1 amps. Ta-da! I figured out one of the currents. I know how much current is going through the alternator. Then you go, okay, you got one. Now what? So from here, I have a few choices. One easy choice, since I know what IA is, I can put it into one of these equations that has IA and solve for the other one. So for example, I might plug it into the W equation now to figure out what IH is. Or I can plug it back into this Y equation to figure out what IB is. Those are two choices. What I typically do is I like to kind of use some of the stuff that I already have, and so I don't want to totally recreate the wheel and try to make it as easy as possible. So I like the idea of plugging this back into W. So using this equation, or even I could plug it into this version of W over here, and I could figure out what IB is that way. So either one, I've used basically everything. I also am a big fan of, once I find IH, maybe coming back up and using that junction rule to kind of finish it out. Either one should work, and that finishes everything for Kirchhoffs rules. I'm going to pause for a second and figure out the rest of these answers, and then go from there. So here's the last little bit, and this is something I think is very interesting to point out. So when I solved this and I figured out the current going through IA, I got 19.1. When I figured out the current going through the headlamps, I got 10.1. But when I solved for IB, I got a negative 9 amps. What does that mean? What does that tell me when it's negative? What it tells me is that my original pick, my original direction was wrong. That up here, when I said that I thought that the current through the battery was going towards the left, that was incorrect. I picked the wrong direction. So this is one of the things I think is very nice about Kirchhoffs rules, is if you happen to pick the wrong direction, the equations are going to tell you. And what's happening is really the alternator is charging up the battery. So it's actually sending more current backwards through the battery to actually create this charge. It's what's causing the battery to be charged. Your alternator is running, it's charging the battery, and it's running your headlamps. If you didn't know this, when you actually have your car running, you could disconnect your battery. Your battery is not actually running all the electronics in your car. It is the alternator that is. That's why if your alternator is bad, your lights will go out and your power will eventually go out, because you're going to drain your battery. So it makes sense that we picked the wrong direction for this, and we could have gone from there. So this is a little bit on Kirchhoffs rules. We'll be playing around some more with these, and I just thought I would show it to you. Hope you enjoyed.